Hi, good morning everyone. Welcome to today's session. Today we'll be just discussing about what is known as a Brayton cycle. Usually this kind of a cycle which was developed by the engineer Brayton is mainly used in aircraft engines, which is a type of rotary engine, unlike a reciprocating engine in automobiles where it is used. Right? It was invented by Brayton, an engineer, and he had patented this design. Also, in this session, we'll be discussing how the Brayton cycle looks like in a PV diagram as well as in a TS diagram. And also, we'll be discussing how to derive the equation for thermal efficiency of a Brayton cycle. Now, before we go into all those details, let me first explain to you exactly what is this cycle all about. Alright. Now here I have marked some components or equipments of that cycle. Okay. So let me mainly tell you what are the main components or main equipments of the cycle. We have a compressor, we have a combustion chamber, we have a turbine, and we have a cooler. The compressor, the function of a compressor, as stated by the name itself, it is used for compression of the air. Alright. Now this compressor, unlike the reciprocating compressor, it has a set of fixed and moving blades and it is a rotary equipment. So here the compression is by means of rotary equipment, not like a reciprocating engine. Alright. Now after the compressed air will come into the combustion chamber. In the combustion chamber, what happens is that air will get mixed with fuel and it undergoes combustion. Now the air that is coming out of the compressor is at very high pressure and temperature, and when it gets ignited, the air fuel mixture expands invariably with very high temperature. Okay, that high temperature which comes out of the combustion chamber is being utilized by the turbine to generate power. For example, as in a electrical generator or as in an aircraft engine to develop thrust. Alright, and then after it expands from the turbine, it goes into the cooler where the air is again cooled and filtered, and then it is recycled back into the compressor. Now this cycle, what you're seeing over here, is what is known as a closed loop cycle. Now in between the compressor and the turbine, one shaft is being connected. Obviously, for running the compressor we need power. The compressor is a power absorbing device, whereas a turbine is a power generating device. Okay, so for driving the compressor, the power is taken from the turbine actually. So how much of a power is being developed or generated by the turbine, how much of work is being done or work is being produced by the turbine, most part of it or most percentage part of it is being used for rotating of the compressor. Hence, what happens is that when this turbine is connected to the generator, so this will be the net work done that we get in the generator. That is the work that is available in the generator, and that will usually be around only 30 to 40% available work, because the rest of 60 or 70% of the work that is developed by the turbine is usually gone for rotating of the compressor or for powering the compressor. Remember, both of them are rotary equipments, and compressor is a power absorbing device, whereas a turbine is a power generating device. Like the compressor, even the turbine has a set of fixed and rotary blades. Alright. And as I told earlier, then after the expansion of the gases, it is fed back into the cooler and then again recycled back into the compressor. Now, usually in practical purposes, it is not a closed loop system. After the air has expanded, it is given away into the atmosphere. It is an open loop system. But for our analysis purpose, for our thermodynamic analysis purpose, we consider a closed loop system. Alright. Having said all these, now let us see how it looks on a PV and TS diagram. If we plot the graph of this work, total work that is being done in this system, we'll see how it can be denoted in a PV and TS diagram, and what are the different factors that affect it. Alright, thereafter then we'll go and derive what is the thermal efficiency. Alright, now let's say we'll take this as point 1. Point 1 is nothing but the point at which air is being sucked into the compressor at normal atmospheric temperature and pressure conditions. Alright, so here somewhere I'll just mark a point 1 on the PV diagram. Now what happens when the air is being compressed? From 1 to 2. 2 is nothing but the air that is being compressed and coming out of the compressor. Now what happens when air is being compressed? Obviously, 3 things happens. The first thing is the pressure increases and the volume decreases. So in this graph, if I have to mark a point from 1 to 2, obviously the pressure increases. So I'll mark it goes linearly up to say a certain point 2. Alright, at a certain point 2. Now this process, what we are seeing from 1 to 2, we are assuming this process to be adiabatic. That is, process 1 to 2 will be adiabatic compression process. Alright, now what is an adiabatic process? I'm not going fully into the details, but let me explain. An adiabatic process is a process where there is no heat rejection or heat supply. Alright, heat rejection and heat supply will not be there. Actually, in practical purpose, that is impossible. But for our analysis purpose, we are assuming that this process from 1 to 2 is an adiabatic process. So from 1 to 2, it is an adiabatic compression process. Alright, now as you can see, when the pressure increases, the volume of the air decreases. So here you can see the volume in this. The x-axis is V and the y-axis is pressure. So as you can see over here, the volume has decreased from point 1 to 2. The volume has decreased from point 1 to 2. You can see that the volume initially was so much, now it has decreased to V2. Similarly, what will happen in the TS diagram? Let's say again I assume a point 1 in the temperature entropy diagram. One more thing you have to remember about an adiabatic process is that in an adiabatic process, the entropy remains constant. For example, like we know Clausius statement, Clausius inequality statement with respect to second law of thermodynamics. That is, the change in entropy is, or S1 minus S2, the change in entropy is dependent upon the heat developed divided by the absolute temperature. Now here, since being an adiabatic process, heat supplied or heat rejected is 0, so delta Q will be equal to 0. Hence, S1 will be equal to S2, or entropy. S1 is nothing but, S1 denotes the entropy. So the change in entropy will be 0. That means S1 is equal to S2. That means entropy is constant. So therefore, in a adiabatic process, actually, the entropy remains constant. Now, since here you can see that in the y-axis it is denoted by temperature and in the x-axis it is denoted by entropy. Now, when temperature increases, I told you, when you're compressing something, the pressure increases, the volume decreases, and the third function is that when you're compressing something, the temperature increases. The entropy but will remain constant since it is an adiabatic process. 1 to 2 being an adiabatic process, the entropy will remain constant but temperature will increase. So let's say from point 1 to point 2, the temperature has increased, but as you can see that the entropy remains constant. The entropy is constant. That is nothing but S1 is equal to S2. Excuse me. Now, the high pressure air coming out of the compressor now enters the combustion chamber. It is here in this combustion chamber that the air and fuel is mixed and ignited. Now what happens is that when air and fuel is mixed and ignited, a lot of high pressure and temperature is created. But one thing what we have to remember here is, this is a constant pressure heat engine. It is a constant pressure heat engine. So whatever high pressure air is coming out from this point outside the compressor, it is at a constant pressure. So if you take points from 2 to 3, we'll see This is the 3. That is where the air after ignition or after combustion, where the air and fuel mixture comes out. Now from point 2 to 3, as I told you, it is a constant pressure heat engine. So from point 2 to 3, the pressure will be remaining constant. From point 2 to 3, the pressure remains constant. Alright, 2 is a high pressure air that is coming out of the compressor, and the pressure of the air that is coming out of this compressor will remain constant. So we can say that from 2 to 3 process, it is a heat addition process, which means to say heat is being added in this process. That means combustion takes place. High pressure air is mixed with fuel and combustion takes place. That means heat is being added, and it happens at constant pressure. It happens at constant pressure. So in the PV diagram, what happens is that the pressure remains constant, and when this gas is heat up with lot of pressure and temperature, obviously the volume also increases. So hence you can see in this PV diagram from 2 to 3, the volume has increased from point V2 to V3, but it remains at a constant pressure. Alright, now what about the temperature? Yes, the temperature also increases very high. The temperature that is produced over here is very, very high. So from point 2 to point 3, what happens is that the temperature increases tremendously. Alright, I hope you're clear up till now. We'll go further. Now, after the hot gases that is coming out from the combustion chamber, that hot gases or the heat energy that is being produced from the combustion chamber is utilized for rotating of the turbine. That means the hot air expands inside the turbine. Alright, the hot air is allowed to expand inside the turbine, thereby rotating the turbine. Okay, so when it rotates the turbine, what happens is that air expands. When air expands, again two things happen: the pressure reduces and the volume also increases. And thirdly, when air is allowed to expand, when hot air is allowed to expand, temperature also decreases. So let's see how this process from 3 to 4 looks like in a PV diagram. So when it expands, as I told you, when hot air is being expanded inside the turbine, what happens? The pressure decreases. So we'll mark it like this: the pressure decreases, and when it expands, the volume increases. So you can see from point 3 to point 4, the volume has increased. It was V3, now it is increased to V4. Whereas the pressure has decreased from V3 to P3 to P4. You can see that the pressure has decreased. Now, once work has been done inside the turbine, or the turbine has produced some useful work, what happens is that air and fuel mixture, by means of some filtration process and a cooling process, what happens, that air is again being recirculated into the compressor. Now these two, like how it happened in the combustion chamber where heat was added. So again I'll just mark this. So from 3 to 4, you can see that it is an adiabatic expansion process. Adiabatic expansion process. From 3 to 4, it is an adiabatic expansion process. Adiabatic, as I told you, it does not allow any heat rejection or heat to be taken. Alright. So an adiabatic expansion process. Similarly, I told you, when it expands inside the turbine, the temperature decreases. And being an adiabatic process, just like how we did from process 1 to 2 for compressor, being an adiabatic process, what happens? The entropy remains constant, but the temperature decreases. Alright, so we have marked it from 3 to 4, which is an adiabatic expansion process. Again, from 4 to 1, the hot air is sent inside a cooler by some condensation method or any other method, by air cooling method. The air is again cooled and then sent back to the compressor, back again for compression. Now again, what happens over here is that the heat removal process, here it was heat addition when ignition and combustion happen, here it is a heat removal process. Both these processes, the combustion as well as the cooling process, what happens here? It happens at constant pressure. Again, the pressure of air coming out over here, we assume it to be at constant pressure when it comes out of the turbine. So constant pressure means from 4 to 1, the pressure remains constant. That is nothing but P1 will be equal to P4. P1 will be equal to P4. And again, when it undergoes cooling, what will happen? The temperature decreases. The temperature decreases. Now here it is expanded air, so the volume increases, the temperature is there. So once it undergoes cooling, what will happen? The expanded air cools. So when some air which is hot air, when it gets cooled, the volume also increases. So that's why the volume also decreases. So that's why we can see from 4 to 1, the volume has decreased from 4 to 1 after it has been cooled. That is nothing but the density of air increases. Okay, so a hot expanded air, when it is cooled, what happens? The density increases, thereby the volume decreases, and therefore from 4 to 1 you can see that the volume has again decreased. And here you can see that from 4 to 1, what has happened is that because of cooling taking place, the temperature has decreased from 4 to 1, that is from T4 to T1. So we can say that from 4 to 1, the process can be explained as a heat rejection process. Heat rejection process. We can call it as a heat rejection process at constant pressure. So this describes how the system works and how the PV and TS diagram looks like, and what are the different kinds of processes in this both PV and TS diagram, temperature entropy as well as the pressure volume diagram. So I hope we are clear with this. Keeping in mind all these processes, we'll go ahead and we'll try to derive what is known as the thermal efficiency of a Brayton cycle. Now, if you look at the thermal efficiency, or for that matter any efficiency, it is nothing but actually it is given by output by input. Alright, it is nothing but it is given by output by input. Now the output is the useful work that we get outside of the turbine. It is nothing but the useful work that we get outside of the turbine. That is the output we need. And from this, it runs the generator, it runs the aircraft engine, providing thrust or electricity as in this generator, whatever it is. But the work done that we get outside, that is the output. So I can write it that the output is nothing but the work done divided by what is the input. Now the input into it is nothing but the heat that is coming out of the combustion chamber. The input to the turbine is nothing but the heat energy coming out from the combustion chamber. So the input is nothing but the heat energy that is being developed by the combustion chamber and fed into the turbine. So we can say that the input is nothing but how much amount of heat is supplied into the turbine. That I will denote it by QS. Alright. Now when we come into what is this work done, here as I told you before, when work is being produced by the turbine, major amount of the work is being absorbed by the compressor. Because the compressor needs to rotate and compress the gases, major amount of the work is being absorbed by the compressor. So the net work done, that is the net work that we get outside, we can write the work done as net work done that we get outside is nothing but the work done by the turbine, how much work is being done by the turbine, minus how much work of that turbine is being absorbed by the compressor. So one is a work absorbing device, one is a work producing device. So it is an absorbing device, we write it as negative because it is absorbing some work. So the net work available over here will be minus how much work is being given to the compressor, or how much energy we have transferred from the turbine to the compressor in running of the compressor. So the work done, net work done will always be the work done by the turbine minus how much work we have given to the compressor, how much work is being absorbed by the compressor. Now we'll again define this term separately. Work done by the turbine, as you can see in this diagram, the work done by this the turbine is between process 3 and 4. Here it is between process 3 and 4 in the adiabatic process. So we know that Q or delta Q, you know that we have learned previously that it is equal to MCP or CV delta T. Delta T denotes nothing but the change in temperature. CP denotes the specific heat at constant pressure, and M denotes the mass of the air-fuel mixture. Alright, the mass of the air-fuel mixture. Now one thing what we have to note over here is why we are using CP and not CV. Usually air, gases, whatever, everything consists, they have two kinds of specific heat. One is what we call a specific heat at constant pressure, and the other one what is known as specific heat at constant volume. But liquids on the other hand, they will not have CV or CP, they will have only CP because it is an incompressible fluid. It is an incompressible fluid as far as liquids are concerned. That session separately I will be taking. Alright, so based on this formula, if you have to write what is the work done by the turbine, we can write it as MCP. Again, I want to tell you why we are using CP, specific heat at constant pressure. As I told before, the air that is being compressed, comes out at very high constant pressure. The air that comes out of the compressor, it's a constant pressure and it is a very high pressure, but it remains at a constant pressure. That's why we are using MCP. Unlike in an auto engine or in a petrol engine thing, where you can see the heat supplied or anything, it will be MCV, means it happens at constant volume. Here, I told you it is a constant pressure heat engine. The pressure of air that is coming out over here is very high, but it is always at a constant pressure. Thereby we are using MCP. So we are using MCP into. Now this work done by the turbine, you can see it is happening between the process 3 and 4. If you look over here, it is between process 3 and 4 in the PV diagram. In the TS diagram, it is between 3 and 4. As you know, delta T, we have to take two variables of the temperature between which it is acting, between 3 and 4. It is acting between points 3 and 4. So we will take temperatures T3 and T4. T3 being higher than T4. So what is the difference of temperature over here? It will be MCP into what is delta T is nothing but the difference in temperature. It will be T3 minus T4. This will be the work done by the turbine. Now similarly, we will have to find out what is the work done by the compressor. In similar terms, you can write work done by the compressor is MCP. Again, work is done by the compressor between points 1 and 2. In the PV diagram it is here, and in the TS diagram it is between points 1 and 2. So T2 being a higher temperature, in the similar terms, it is between these two temperature differentials it is working. So we can write it as T2 being higher, we will write it as T2 minus T1. So we got the work done by the turbine in terms of temperature and work done by the compressor in terms of temperature. Alright. Now we have to find out what is QS or what is the heat supply. Alright, we'll also do that. Now if you look in this diagram, you can see that the heat is being supplied to the high pressure compressor air between points 2 and 3. The heat is being supplied between points 2 and 3. So here it is between points 2 and 3 in the temperature entropy diagram. So same heat is also being supplied at constant pressure, and MCP into the difference that T3 is higher than T2. These two differentials will take and we'll write it as T3 minus T2. We'll keep this as equation A. This one we'll keep it as 1, 2 and equation 3. Now let us substituting equations 1, 2 and 3 in equation A, and we'll see what we'll get. So thermal efficiency is nothing but work done is nothing but net work done by the turbine minus work done by the compressor. So I'm just going to substitute these values what you have written over here. Work done by the turbine is MCP into T3 minus T4 minus MCP into work done by the compressor T2 minus T1, the whole divided by what is the heat supplied. Here we have written MCP into T3 minus T2. Now MCP being common, we can just cancel it out, and again we'll get thermal efficiency is T3 minus T4 minus T2 minus T1, the whole divided by T3 minus T2. Now I'll just bring this equation in terms of T3 minus T2. I'll just see if I can get the same denominator function in the numerator also. I'll just rearrange these functions. I'm not doing anything much. I'm just rearranging these functions. So I get T3 minus T2 also one function in the numerator. That's for just a simplification purpose. That's all. So I can write this numerator again as T3 minus T2 minus T4 minus T1 whole divided by T3 minus T2. I can further reduce this. I can further simplify this equation. This equation I can write it as again T3 minus T2. You can see that both numerator and denominator are both these functions together. So I can write this one as 1 minus T4 minus T1 divided by T3 minus T2. It's nothing, it's the same function. All these are the same, but I've just simplified it. That is nothing. If you take the LCM, you will get this. If you take the LCM and you do this, you will get the same equation. And if you rearrange it back, you will get the same equation. For simplification purpose, I just simplified it into this. So again, our final thermal efficiency equation, we can write it as 1 minus T4 minus T1 divided by T3 minus T2. This is the thermal efficiency in terms of temperature. Now, actually in question papers or in academics, when they ask you this question to derive the thermal efficiency of a Brayton cycle, usually you should not stop over here. Actually, you should derive it in terms of pressure ratio. Okay, we'll see how to derive it in terms of pressure ratio next. So I hope I'm clear up till here. So we have derived the thermal efficiency as this. Now we'll see how we can derive it in terms of pressure ratio. So for that, first let me explain to you what is a pressure ratio. Now, we have something what is known as a pressure ratio. It is denoted by usually by R suffix P. Pressure ratio is nothing but P2 by P1. As you can see over here in this PV diagram, it is the ratio of P1 to P2 or P2 by P1. It is the ratio of pressure at when it is finished compression and when the compressor sucks in the air at atmospheric pressure and temperature. So this ratio between P2 by P1 is what is known as a pressure ratio. So whenever they ask a question to derive the thermal efficiency of a Brayton cycle, then it is not enough if you stop at this. You have to derive it in terms of pressure ratio. Let's see how we can derive it in terms of pressure ratio. For that, we have something what is known as the PVT relation. Okay, I'm not going to explain this because in the next session or further sessions, if you have any doubts, I will explain this, how to derive PVT equations. PVT equations are nothing but equations which have these three factors of pressure, volume and temperature and how they are interrelated by mainly three laws. One is the Charles law, Boyle's law and universal gas laws. By combining all these laws, we can get different functions of pressure, volume and temperature related to each other. So, as per the PVT relation, which I am not going to derive again because it will require one more full session to describe that. Assuming that you know about this PVT relation, I am going ahead. We can say that from the PVT relation, T2 by T1 is nothing but P2 by P1 whole raised to gamma minus 1 by gamma. This relation, it can be got by PVT relation. If you have time, you can itself derive it. You can see we use Charles law, Boyle's law and universal gases law, and then you can derive this equation. You can find out that T2 by T1 is P2 by P1 whole raised to gamma minus 1. Okay. Now, but P2 by P1, as I told you, P2 by P1 is nothing but pressure ratio. So I'll write it as pressure ratio raised to gamma minus 1 by gamma. Therefore, we can rewrite this as T2 by T1 is equal to pressure ratio whole raised to gamma minus 1 by gamma. Okay. Now next, again, now what I'm trying to do over here is I'm trying to get an equation which I have derived already in terms of temperature. I'm trying to get this equation in terms of pressure ratio. So that's why I'm doing all these exercises. That's why I'm trying to convert T2 by T1 into pressure ratio. Similarly, what we'll do next is T3 by T4, again using PVT laws, T3 by T4 is nothing but P3 by P4 whole raised to gamma minus 1 by gamma. Now if you look carefully, if you come back to this PV diagram, we know that P3 is equal to P2 because it's a constant pressure process. So P3 is equal to P2, and we know that P4 is equal to P1. Again, it is being a constant pressure process. So I can substitute P2 instead of P3, and I can substitute P1 instead of P4. So substituting this, I can write this again as, which is nothing but P2 by P1 whole raised to gamma minus 1 by gamma, which is nothing, again P2 by P1 is nothing but it is the pressure ratio. So again this is also can be written in terms of pressure ratio. So you can see that T2 by T1 is actually equal to T3 by T4. T2 by T1 is actually equal to T3 by T4. How we got it? Because P3 is equal to P2 and P4 is equal to P1 from the PV diagram. So I substituted it and I got it the same equation. So when I'm getting the same equation, obviously T2 by T1 will be equal to T3 by T4. So we'll write it down. So we'll say T2 by T1 is equal to T3 by T4. Now my main intention is I have a T4 over here. I have a T4 over here and a T2 in the denominator. So I try to bring T4 up and T2 down, so that I can get some term which I can substitute with pressure ratio. So I can see that T4 is in the numerator. I will just cross multiply, and if I cross multiply this, I can get the equation as T4 by T1 is equal to T3 by T2. So now I got the equation. I just cross multiplied it. So I'll get T4 by T1 is equal to T3 minus T2. Now furthermore, I'm just going to do one more step. It's nothing complicated. What I'm going to do is in T4 by T1, I'm just going to add a minus 1 on the LHS. I'm just going to add minus 1 on the LHS, and I'm going to add a minus 1 on the RHS also. I'm going to add a minus 1 on the RHS also. So it will be the same. The equation will be the same. If I'm adding 1 and 1 on both sides, it will get cancelled. So it will be the same. But I'm just adding it. That is to get this term. Main thing is I want to get this term. That's why. So now if I take the LCM of this LHS, I will get it as T4 minus T1 divided by T1. If I take the LCM and do it, I'll get it like this. And here I will get it as T3 minus T2 whole divided by T2. So now I got some terms. I got T4 minus T1 over here, and I got T3 minus T2 over here. Now again I will just cross multiply it, so I will get this term over here. We'll see how it is done. Nothing much, it's nothing hard to do. I'm just going to cross multiply this, and nothing much complications in this. I'm just going to cross multiply this equation. So when I cross multiply this equation, I will get T4 minus T1 divided by T3 minus T2, and this T1 will come here, so it will become T1 minus T2. Now almost our equation is complete actually. You can say that our equation is complete. Now if you look here, you can see that T2 by T1 is Rp raised to gamma minus 1 by gamma. So T1 by T2 will be the reciprocal of this. Okay, so T1 by T2 will be the reciprocal of this. Reciprocal of this is nothing but 1 by pressure ratio raised to gamma minus 1 by gamma. So I got an equation T4 minus T1 by T3 minus T2 is nothing but 1 by pressure ratio whole raised to gamma minus 1 by gamma. Now I have got this equation in terms of pressure ratio. Understand that I first got this equation equated to T1 minus by T2, and you know that T2 by T1 is pressure ratio, so T1 by T2 will be the reciprocal of this. So now we have got a final equation. So finally we can write that. Thermal efficiency is nothing but 1 minus 1 by Rp raised to gamma minus 1 divided by gamma. So this is a final equation. If they are telling to derive the thermal efficiency of a Brayton cycle, you have to derive up till here. You will have to draw the diagram, you will have to draw the PV diagram and TS diagram and do all this and then derive it in terms of pressure ratio. I hope the session for you students was useful. If any other sessions, many sessions I'll be taking, for example, PVT relations and many other sessions also I'll be continuing to take further classes. Okay, thank you everyone. Thank you.